Yeah. So what we were discussing in the previous class is wrote. Uh, Sorry. Okay. Wait. Hmm. I wrote the topic of my course as relativistic universe. Okay. And what does it mean? It just simply means we are studying, okay, general theory of relativity, okay, uh, in a four-dimensional space-time, okay, or we call it 3 plus 1 dimensions. It is time, coordinate, and there are three spatial coordinates. This is in Cartesian form. Okay, fine. Then we just studied that how GR can be translated to SR in weak field limit. Okay, we are just recapping things. So recap, and then how can SR be further translated to Newtonian relativity in slow motion limit? Okay, and another thing is Newtonian gravity. Okay, when these both are applied, both limits are applied, weak field plus slow motion, the things can be translated to Newtonian. Okay, so this is my general relativity. We will come to it, but we will start with Galilean relativity, or say Newtonian relativity. It is also called Galilean relativity because the first principle of relativity was given by Galileo. Okay. Then we just distinguished what is the difference between GR and SR. Okay. We made a table and there were some points we will understand that uh, throughout the course. Then we just define what is a geometric object. Okay, it is geometric object. Let me write it more clearly. Object. It is something that is independent of representations of frames of reference, our reference frames, reference frame. And a reference frame is defined by a clock, that is a time coordinate, and some spatial coordinates. This is in Cartesian or in r theta phi, whatever you choose. Okay, these spherical coordinates, these are Cartesian coordinates. Okay, this we were talking about. Okay, and the examples of geometric object were like events. Okay, so event E can be defined as XYZ in S frame, suppose, and suppose in E dash A prime frame, suppose it is defined like this. So this is S prime frame. So these events are actually geometric objects that are independent of the representations. And secondly, we talked about vectors. Okay, so we have discussed this all. So a vector V, we will come to it again. A vector V one in can be written as in S frame can be written as this. Okay, or it is same in this is in S frame suppose. Okay, and similarly, it can also be written in prime frame with different components. Okay, so components and its uh, unit vectors will change depending on the frame, but magnitude and its actual direction is actually the property of a vector, intrinsic property of a vector, and will not change. Okay, the total magnitude. Now, also, this was my first example. This is second example. Let's talk about some tensor thing. Tensor is also a geometric object. Okay, so suppose let's take rank 2 tensor. Okay, first of all, uh, okay, rank 1 tensor, rank 1 tensor, or say rank start from 0. Let's start from 0. Okay, rank 0 tensor is also called a scalar, and rank 1 tensor is also called a vector. Okay, rank 0 tensor is a scalar and rank 1 tensor is a vector. So let's construct simply a rank 2 tensor. Okay, I will construct a rank 2 tensor and I will denote it by two arrows. Okay, why? Because I am constructing, I can construct a second rank tensor with two vectors, by two vectors, and this product is called a tensor product. Okay, this product is called a tensor product. Suppose this was my vector representation, and suppose I have a vector 1. Okay, that is of course that is yes, this one, this is a3, and suppose I have a vector 2 like this. Suppose let's give it b. Okay, b1. Let me just write b1. Okay, it's e1. Okay, it's b2. It's e2, and you know what are these e1, e2, and e3 are? These are unit vectors. This is p3. Okay. Now, what is the tensor product of these both? Okay. This is my two vectors notation. I'm constructing a second rank tensor using these two vectors with a tensor product. So I can write this. Okay, this is my first vector, and I will do a tensor product it with second vector. You able to listen me, right? My voice is clear, right?
Yes.
That's fine. So what we will do, how do we define this product is to take the first one and multiply with this whole vector, all three components. Okay, this first one. And then we will take this one and then again we will multiply with this whole second vector and then one by one. Okay, so it will be like a1, b1, e1 tensor product with e1. Okay, then it will be a1, b2 tensor product with of a1 with e2. Okay, you can continue this. Okay, let's write it down then. A1, b3, it's easy to write. Okay, so okay, let me type. So now this will be 2 b1. I guess I'm going right. It's b2. Okay, 2 b1. Yes, it's b2. I'm writing this for completeness, and it will help us in future. And again, this is b3 e1 2. You are writing with me, right? Just write with me. Help with me. Okay, so this is my tensor of rank 2. Means there are two vectors I'm using to construct a tensor. Okay. Now there are some key properties of this tensor product. Say the key property is the commutativity. Commutativity. Okay. For a tensor product, okay, these EI unit vectors are not do not commute. Okay, in general, they do not commute. They do not commute. Okay, so applying first this direction and then applying this direction is not same as applying I and then after then J. Do not commute in generality. Okay, in general. But suppose I take a cross product. You have studied in your previous classes. Okay, so what is a cross product? How do they commute? Do they commute or not?
Anti-commutation.
Yeah, they are actually anti-commuting. Okay, this is just a cross. Okay, no circle over it, so it is a cross product and they anti-commute. Wait, and they anti-commute. Right. And there is a scalar product. Do they commute? Do this commute?
Yes. Yes.
So yes, they do commute. Okay, and they both do not commute. Cross product do anti-commute. Now we can define this. We can simply write, wait, hmm, define a tensorial direction. Okay, define a tensorial direction, that is EJ is the product tensor product of EJ I and EI and EJ. Then we can simply write our tensor. Okay, after writing this, we can also write this tensor as EBJ. Oh, okay, let me write it completely. What was our tensor in vector? It was the tensor product of V1 and V2. Okay, and if I expand this V1 and the basis and its basis, okay, so I can write this as AI BI summation. This is summation from I goes 1 to 3 AI and E. So, you got it right. This is summation I3, okay, with AI and EI. Similarly, for V2, is a summation from 1 to 3. It is BI and it's okay. You can write it J. It's better to understand. Okay, so when you write here, it is from 1 to 3. Okay, it's AI BJ cross tensor product with EJ. Okay, so we can also define something like a tensor component like this. For now, it is a product of these two components only. Okay, so how will my tensor look like now? It will be the summation over I and j from 1 to 3. Okay, Tij and Eij. Okay, I have defined my tensorial direction like this. Okay, so this is my tensor. Okay, as a linear combination of its tensorial directions. This is a expanded form, expanded form of rank 2 tensor, right? So also you will notice when you expand this, okay, when you expand this, you can see you will here find T11, here T12, T13 and all, and you can make a matrix out of it. Okay, so you can make a T matrix out of it with the all the components T11, T12, T13, T21, T22, T23, T31, T32 and T33. Okay, so this is a matrix form. The components of a tensor. These are components of rank 2 tensor. Okay, in matrix representation. In matrix representation. Okay, so you understand what is a tensor now, mathematically. Okay, so a tensor is also a tensor is also a geometric object. Okay, means just like just like vectors. Okay, just like vectors, suppose it is my S frame and it is my S prime frame. Okay, so a vector can be written as AI in S frame and it is same as in S prime frame will be A prime, it will be E prime. Okay, similarly, we can write a rank 2 tensor. Okay, rank 2 tensor. Okay, how will I write this? I and j summation 2 up to 3. Okay, so it is t ij. It's t ij and it is eij. It's direction, tensorial direction, and it should be same in the S prime frame. It's just different representations of it. Okay, so in the previous class we have wrote I have given you some question regarding the magnitude of the vector. Okay, there I had a vector which had some representations. Okay, and I told you that these representations are equivalent. Okay, so if my magnitude of this vector, suppose in representation 3, it is 3 units. So in all frames, it must be 3 units. In representation 1, it should be representation 2 also, and in representation 3 also. Note that this equation does not signify that these two directions are equal, but they are equivalent, of course. I mean, you cannot equate, these are representations. Okay, these are representations. These are representations. So, of course, you can write this like mathematically they are equivalent, same direction, same direction. Okay, now you can see like this. Actually, okay, this let me write this as cap. Okay, what can you remember what was it in at the last class? It was this in representation 1. Okay, and it is same as it is equal to in representation 2. It was similarly like this, and similarly it was Ez in the third representation. We were talking about the example we discussed in the previous class. Okay, now you see here when you see this explicitly, this is my one in first representation is equals to 3 by 2 second representation is equals to this in second representation. Similarly, it is like this. So what did you notice? Components or directions, say unit vectors, actually depend on the representations. But the overall magnitude of a vector and its direction. Okay, these are also basis. We can call it basis. Okay. This direction is not actually basis one. Okay. This is overall direction of a vector is intrinsic to a vector. Okay, so the direction will not change in any representation, but its basis directions can change. Okay, fine. Let's move ahead. So there's a question again for you. Okay, answer question. So you understand that, right? Yeah, this is reference frame one. Okay, this one is reference frame two. And this one is reference frame three. Okay. Mhm. There is a question. Okay, consider a rank 2 answer. Okay, that is T defined as E1 one direction plus 3 E1 two direction. Yeah, that is just means 4, not 4, it's just, okay, let's take it this 1 2 direction, and this one is 4 E2 direction. Okay, firstly, write components in matrix form. Okay, just write it in matrix form. Secondly, if the new basis, if the new basis is related to old basis such that new basis is suppose prime frame, okay, and the old basis is suppose my unprimed frame, is related by a rotation matrix, Let me see something else. Fine. Okay. Matrix, rotation matrix, and the matrix is 1 minus 1 plus 1. Okay. Then, and the relation, it is okay. So it is related by the relation, that is, this is my matrix in prime frame, and this is my rotation, transformed rotation matrix, and this is my tensor matrix. Then we must calculate T prime, okay, in prime frame, the matrix. It's easy, you can do it, right? Third, verify that although this matrix and this transformed matrix are different, okay, but but they represent the same tensor, the same second rank tensor. Okay, so any questions till now? We have completed with this tensor things. The
Can you explain the B part of the question again?
just you have to verify, ठीक है? Verify that these metrics when you compute,
The
when you
B.
will compute B1.
Uh,
Okay, so this is my new basis. Okay, it means suppose this was my old basis, suppose this is my old basis, okay, reference 2 is my old basis, and I do some transformation to this basis. Okay, I do some transformation to this basis. I by applying that transformation, I am getting this one, the basis, as the basis. Okay, so by applying a transformation matrix, I am going from reference to basis, that is ex2 ez2, towards the reference 1 basis, ex1 and ez1. Okay, by applying some transformation, you can just translate your these basis things from one reference frame to other. You just have to check. I have given you the relation. This is my relation, transformation relation. This is my transformation relation, and we will see uh, the Galilean transformations now. And you just have to calculate this T translated, sorry, transformed matrix of tensor. Okay, second rank tensor. Is it fine?
yes.
Yeah. So then you have to verify that these two matrices will be different, but actually they represent the same second rank tensor. How do you verify it? You have to think about it. Okay, let's move ahead. So now we will study the Galilean transformations. Finally, we are coming to Galilean transformations. Okay, these are simple transformations when we relate our physics in the slow limit to from one reference frame to another reference frame. Okay, so let's do this. Just do it. Okay. Suppose I have two reference frames. Okay, this is my first reference frame, and I call it S frame. Okay, this is my x-axis, this is my z-axis, and this is my y-axis. Suppose. Okay, I am again taking the left-handed coordinate system. Okay, I have told you in the previous class what are left-handed and the right-handed coordinate system. So you can, I mean, just hold your this z-axis with your left hand and curl your fingers from x to y. You can do this easily with your like left hand, but with right hand you cannot like go from X to Y, and your thumb will be pointing in this direction for Z. Okay, thumb direction should be Z direction. Okay, in right coordinate system, right handed coordinate system, this will be opposite. Hope you understand that. If anything is unclear, just tell me. Okay, this is my left hand coordinate system, and this is my S frame. And suppose I have another S frame, S prime frame. Okay, and both the frames are initially at time zero. At time zero, they are coincident. These are X prime, Y prime. These are coordinates of my, and this is T prime and T. Okay, I have to consider the time coordinates also to study my physics. Okay, because that's how we define our events. And suppose, okay, at time t, at time t, these frames are like this. This is my x, y, and this is my z. Oh, sorry, mistake. Yeah, this is z, this is y. This is my s frame. And now the s prime frame just translated. Wait, this is, why is it happening like this? Okay, this is my, okay, this is x, this is my z, and this is again my, well, this is prime, this is prime, and this is s prime frame. Okay, and this s prime frame is translating in the x direction. Okay, in the x direction, this is my o origin, this is my o prime origin. Okay, can you tell me after t time how much the distance will be covered? What will be this distance after t time?
Vx multiplied by t.
Yeah, of course, the distance is Vx multiplied by t. Okay, let's denote it by r vector. So this is will be by r vector, which is dependent on the time. Now suppose there is some like event happening here. Okay, and in the in the s frame, I will write it by this coordinates, and in the s prime frame I will write it by prime coordinates. Okay, now just make, okay, so let me draw it separately. So now from O origin to O, this is O prime origin. Okay, and this is my E event. Okay, or say, yeah, this is my point, E point. I will draw a vector from here to here, and let's call it R vector. And I join this vector to this vector. Let's call it R prime vector. And what is this vector we have defined already? This is my R vector, which is time dependent. Okay, so what is the triangle of vectors? Hmm? What is the triangle of vector? It's basic 12th class law. What is it? How will the equation look like? It's a triangular
Capital R
transformation.
vector,
Yeah,
capital R vector plus R prime vector will equate to R vector.
equate to r vector. Yeah, right. So this can further be written as r prime vector as r vector minus vxt, right? Because my r, capital R, is vxt. So this is my main equation. It's a simple equation and a main equation. Okay, there is something else we consider in Galilean relativity, that is absoluteness of time. You can consider it as the first postulate of Galilean relativity or Newtonian relativity. In this, Newton considered that time is always absolute. Time is always absolute. No matter where you are in this universe, for you and anyone who is very far from you in this universe, both the time will pass the same. Okay, if you tell your friend that the event will happen at 12 o'clock and your friend is very far, suppose outside the Milky Way galaxy, for him also in Galilean relativity, okay, the time will be at 12. If you will both agree that that event will occur at 12 p.m. Okay, if one if in your frame the event is happening at 12, then in your friend's frame the event will also happen at 12 o'clock. And this also implies that del t dash is del t. This is absoluteness of simultaneity. Absoluteness of simultaneity. Okay, if there is a difference between two events in your frame and it is suppose of 2 hours, okay, difference between two events, suppose one event happened at t1 and second event happened at t2, the difference will be del t. Okay, in your frame and your friend's frame, okay, it will happen at equal intervals. This is simultaneity, and it is obvious to all of us that this happens in our daily life daily. Okay, this is simultaneity. Let me do this. Equation 1, this is equation 2. Okay, so I can write in explicit txyz coordinates. Equation 1 as, you can find it out, okay, by putting your vectors, like what is your vector? This is xk, this is in y direction, and this is in z direction. Okay, when you put this in your first equation, you will find this coordinate equations. There is no velocity in the y direction, so there will not be any change in the y direction as well as the z direction. Okay, also this is my another absoluteness we are assuming in the theory. Okay, and these are what we call Galilean transformations. These are simple transformations. Okay, Galilean transformations. Okay, these are simple transformations. Any questions till now? Okay, from here we can define primarily, you know, in a most basic sense, we can define some four vector notation. Okay, some four vector, and it is just a vector with four components. Okay, a vector with four components and four directions. Components with sorry with four four components and four directions, or say basis directions. Four basis. So, basis vectors. Unit vectors are our basis vectors. So we can write a four vector like this. Suppose this is a four vector. I will denote it by like this. Okay, there are two lines here and an arrow. Okay, let me write it again clearly. This is only my notation. You will not find it in any book because I just need to explain things in simple. Okay, again, that was a tensor, but this is a four vector. Why I have defined this notation? Can anyone explain this? Okay, this is my t component, and let me write this component with 0. Okay, this is my t component plus a1 with x component plus a2 with y component plus a3 plus z component. Okay, you can also write it in matrix form like in a column vector as a0, a1, a2, and a3. This is my four vector. Okay, and this signature represents my matrix representation. Okay, this signature in the dot over is actually for representation. Sorry, matrix representation of anything. So matrix representation of my four vector is like this. Okay, so what is the difference between this arrow? This is a vector, three vector, or say three vector. This is my four vector. This is not actually a standard notation, but I am defining this one. Why I have defined it this like this? Because when you construct an arrow, you will need three lines at most. Okay, three lines at most. But when you consider a four vector, you will need four arrows, four lines. Okay, representing your four dimensions. So this is uh, what I introduce to myself, that it is better to write this, but we will have to follow the standard rules. Okay, we will come to like other notations lately. So now for the time being, let's write the equations, the Galilean transformations Just write with along with me. Otherwise, you will fall behind. Okay. The Galilean transformations can be written like in the matrix form like this. T prime. Okay. First we consider it as a standard convention. Okay. We take the time coordinate first and then the spatial coordinates. Okay. And then this is my vector in prime frame. And this can be written as a transformation matrix. Okay, minus Vx. This is again 0, 1, 0, 0, 0, 0, 1. Applied on my S prime vector, that is t, x, y, z. Okay, fine. These are my space-time vector. It is my space-time vector. I call it space-time 4 vector. Such that this 4 vector in a matrix representation is given by in prime is given by this. Okay, and I have a suppose I like define a G matrix. This is my Galilean transformation matrix. You are understanding things right till now. There is no I mean hard thing to accept these things. I am just defining these things this way because it is useful in studying complex systems, and I mean the four vectors are intrinsic to the spatial theory of relativity, and the whole theory is formulated in four vector language. Okay, oh, sorry, I'm sorry, I should write this separately. Okay, this is my four vector again in S frame. So in compactly we can write Galilean transformations as simply my four vector notation as G, okay, with a simple matrix multiplication, okay, in a prime coordinate, and this is unprimed system coordinate system. These are simply my Galilean transformations in four vector form. Okay, is in four vector form. Fine. Now you have to do one thing. Okay, there is another question. Just it's a simple things I am giving you. Don't worry. Okay, so this is equals to this. Okay, you can get it from the above equation. Okay, when I consider that G is invertible matrix. Okay, just find this inverse matrix and and show show the inverse. Okay, I should write it. Okay, the form. Show the inverse Galilean. Okay, the Galilean transformation equations. equations are, can you guess what will it be? These are simple. Can somebody guess what will be the inverse equations? These are
V
simple, man.
plus Vxt instead of minus Vxt in the x component.
Yeah, these are simple. Just have to find the inverse of the matrix, or you can just write it these equations from your first equations directly. Just you need to consider the right reference frame to write these equations. Okay, earlier we just have the prime coordinates here, and the all coordinates here in the right hand side were unprimed. But now the left hand side considered only unprimed coordinates, and the right hand side only considering the prime coordinates. Okay, so these are my inverse, and I can write as PGT, inverse Galilean transformations. Okay, so you just find that inverse matrix, okay, explicitly, and check, verify these are these inverse Galilean transformation. Now I will take a few more minutes, okay, because I need to complete this Galilean thing. Velocity addition rule. Velocity addition rule. What is it? You can just simply from these equations, um, these Galilean transformations, you can write the velocity laws either by differentiating, or you can just take the difference between the coordinates. Okay, so you can do this like from your from first equation. Just define it like this, where v is constant. Okay, v is constant. Why v is constant? Why v is constant? Why not it is variable? Explain. I have told you before this. Why the velocity of S prime frame is constant?
Because these things don't apply on the non-inertial frames, so
Yeah,
acceleration cannot be present.
because yeah, S and S prime frames are inertial to each other. To each other means from one any one of them, okay, relative to any one of them, the other will be moving with a constant velocity. You can take also this. Where is it? You can also take observe things. When you will be observing things from the S prime frame, this frame will be moving in the negative x direction with the same velocity but opposite direction. Okay, so you can find the same, you will find the same equations from that also, but with inverse as your prime, these inverse as your main Galilean transformations, and the inverse of it as these transformations, because the velocity, the direction of the velocity has now changed, it's now opposite. So you can just quickly write the velocity form by dividing this is my u x prime. Okay, what will it be? Hmm? T prime, and we, by the absoluteness of the simultaneity, this is 1, of course, and this is of course delta t. It will be equal to ux. Okay, so minus v, ux minus v. And consider since my delta t dash is this. Okay, what about uy? Will they change? This time will not change. This is my uy. Similarly, uz will not change. Yeah, these are my velocities. So what you get? So velocity transformations, velocity transformations are u x prime is equals to u x minus v, u y prime is equals to u y, u z is equals to u z. These are simple equations you have studied in your which class? 11th class, I guess. Have you studied these kind of equations in 11th class?
Yes.
Which chapter?
Laws of motion.
Yeah, and the laws of motion, and at the last page, I remember there were some questions related to it also. You just remind it all. These are just basic equations. Okay. Okay. And acceleration transformation is very simple. You just can find or how the acceleration transform. You just differentiate both sides. Okay. You will find that the acceleration in both frames will be equal. Okay. These are components. These are components. This implies the A vector in prime frame is equal to A. And when you multiply the mass both sides, you see that F prime vector is F. So in both frames, your forces are equal. No change in force, no transformation in force, no transformation in force equations. This also implies that my laws of physics, that are Newton's laws, or you can check other laws too, like conservation of momentum and all. The laws of physics is invariant under Galilean transformations. Under these kind of transformations, the laws are invariant. And this is the famous principle of relativity given by uh, Galileo. Okay, Galileo Galilei. So I can write this principle of relativity. Uh, I will end this class after this. Okay. So the principle of relativity is given as that all laws, all the laws of physics are say have the same form, have the same form or same in all inertial frames. Okay, okay. This was given by Galileo Galilei. This is the- This is the main principle of relativity. We Hana, note that. Note this principle. We will use it, this principle of relativity, or say the Albert Einstein used this principle of relativity as the first postulate of the special theory of relativity. Okay, so this is my main consequence of it. Okay, so what this principle of relativity says, that signifies that no experiment, there is no experiment performed, you cannot perform any in uniformly moving laboratory laboratory. Suppose you are in a constantly moving train. Okay, you can imagine you are constantly moving train. So no such experiment, no any experiment can be performed in a uniformly moving laboratory, है ना, that can determine the laboratory whether the laboratory is at rest or moving with a constant velocity. So this is all for now. Okay. So any questions till now? Did you understand what we have just discussed from starting? Any questions? Just think about it. What you have written. No questions. Shall I ask then? This was too simple, or I oversimplified things. So is it easily acceptable, like principle of relativity for to you? Think what Albert Einstein have faced to like discard things in the Galilean transformation, Galilean relativity. Although he included this principle of relativity, there was something like that we do not use the Galilean transformations at high speeds, but these are only valid at low speeds. Okay, so I can also, you can write this here in low speed, low, okay, slow motion limit. These are only valid at slow motion limit. We will see why these transformations will change their form okay, in the fast motion limit. And we will see that these transformations or such transformations at high speeds will signify that space and time coordinates are actually interconnected. You can see here that these are not actually connected. Only the spatial coordinate includes the time coordinate, but the time coordinate do not have any spatial dependence. You can see here. Okay, so time coordinate is independent of the spatial coordinate here. Okay, but the spatial, of course, we have seen the like x. I mean, changing the frames. We have seen that it is dependent on t prime. That this the position in s prime is dependent on the time of the s prime frame. Okay, but there is no such dependence in the time. So we will see that this is very interesting, and we will just see and train example in next class. Okay, we will end this class now. So in the next class, we will just see an example for of this Galilean relativity. That is what is it? Yeah, projectile motion. Projectile projectile motion in uniformly moving train. Okay, you can think about it till the class. What will how the physics looks or how the physics changes when we see a projectile motion in a train or with respect to a projectile motion at ground. Okay, so Galilean, you just find if you can the mathematics behind it, that we will do in the next class. Okay, so let's end this class here. Okay, thank you.